let's take a look at our final type of related rates problem. So, the problem says, suppose liquid is pouring through a cone-shaped filter that has a radius of 4 inches and a height of 16 inches. If the liquid is flowing out at 2 cubic inches per minute, how fast is the depth of the liquid changing when the level is 8 inches deep? Okay, so I'm going to start off by drawing a picture. So we have a cone-shaped filter. So we're going to assume that it is circular at the top, and then the cone is facing downward. Okay, so there's our filter. Now what do we know about that filter? We know that it has a radius of 4 inches. So this distance here, that r is equal to 4 inches, and that's a fixed value. And then we have that it has a height of 16 inches. So this distance here, this is 16 inches, and that is also a fixed value. What else do we know? So we know that liquid is pouring through the filter, and it's flowing out of the filter. So you can picture it like there's liquid coming out this end. Okay? It's flowing out at a rate of 2 cubic inches per minute. Now because it's cubic inches per minute, that's talking about volume. So the liquid is coming out at a rate of 2 cubic inches per minute. Okay. Because it's coming out and not going in, this is going to be a negative 2 cubic inches per minute. Okay? And it's dV dt, again, because it's a cubic unit. All right? And something cubic automatically goes with volume. Okay. So now the question is, well, what's really happening inside here? So we have this liquid level in here. And there's a height associated with that. We'll call that h. And there's a radius associated with that going this way. Actually, let's make that a different color so you can really see it. I'm going to call that r. Okay, and this r equals 4 inches up top. I'm going to change that. I'm going to make it just say 4 inches because that's a fixed number. We don't need to worry about that changing, so it doesn't need a variable. So let's just go back and adjust that, and we'll just make this 4 inches. That's fixed, so it doesn't need a variable. Okay. So what do we do from here? We know that we're going to end up having the level be 8 inches deep. So this h is going to be equal to 8 inches. So we have 8 inches for h. We have negative 2 cubic inches per minute for dV dt. We're going to need a volume equation. So the volume of a cone is equal to 1/3 pi r squared h. Okay, remember that formula will be provided to you. You are not responsible for memorizing that. But when I look at that, I see the v, so we'll have dV dt, which was something we were given. But there's also an r and an h, which means when we do the derivative, we would have to do product rule, which means we're going to get dr dt, which we don't know, and dh dt, which we don't know. So there are too many unknowns here. So what we're going to need to do is we're going to need to figure out a way to simplify this equation so it's in terms of just one variable instead of two. Instead of having r and h, we want to have just r or just h. All right? So in order to do that, we're going to use similar triangles. So let's take a look at the cone picture one more time. If you picture the blue cone cut in half, you would have this triangle, where we know that the top radius was 4 inches and the height was 16. And this is a right triangle. Now if you look at the green, we would have another triangle, and it's going to be a similar triangle, and that's going to be h and r. So what we're going to do, because these two triangles are similar to one another, we're going to go through and we're going to write a proportion. Okay? So our proportion will be this. The height of one in comparison to the radius of the other. So it would be the height of the blue one is 16, the radius is 4. Okay? So h divided by r is equal to 16 over 4. or just 4 over 1. We're going to use this to substitute up in the green equation, the 1/3 pi r squared h up here. Okay? The question now is, what variable do we want to get rid of? Do we want to get rid of r, or do we want to get rid of h? And that depends on what rate we're looking for. So let's go back and look at the word problem one more time. At the end it says, how fast is the depth of the liquid changing when the level is 8 inches? So we want to know how fast is the depth of the liquid changing. The depth here is that h. So I want to keep the h and get rid of r. All right, so here's how we do that. Let's start fresh. So we have our equation, volume equals 1/3 pi r squared h. And we now have our proportion, which says h divided by r is equal to 4 over 1. And we want to get rid of r. So I want to solve this for r. So I'm going to cross multiply. H times 1 is h. 4 times r is 4r. So r is equal to h divided by 4. So now I can take this h divided by 4 and replace the r in the original equation so that it's all in terms of one variable. So this equation is now going to become volume equals 1/3 pi times r, h over 4, squared times h. And we're going to simplify that completely before we do any derivatives. So again, we're going to have volume equals 1/3 pi. This part is h squared over 4 squared, which is 16, and then it's still times h. I'm going to do the 1/3 times the 1 over 16 to get 1 over 48, and then pi, and then h squared times h is h cubed. So this equation is the same as the 1/3 pi r squared h for this particular problem, but now I have it in terms of one variable on the right-hand side, so I can avoid product rule and I won't have too many unknowns. Okay. This process with the proportions is going to happen every single time that you're doing a cone problem. It always has this proportion that you have to set up and solve, and you always need to replace one variable. Okay? So now from here we go through and we do our derivative. So the derivative, dv dt. The 1 over 48 pi stays because it's a number times something, and then I do the derivative of h cubed is 3h squared dh dt. All right, and if I clean that up just a little bit, 3 over 48 is 1 over 16. And then I have the pi h squared dh dt. And this is still equal to dv dt. We're going to plug in everything that we know and then go through and solve for dh dt. Okay? So what do we know? We know that dv dt is -2. We have 1 over 16 pi. And we know that h was equal to 8. And what we don't know is dh dt. So I'm going to simplify the right-hand side. So 8 squared is 64. 64 times 1 over 16 is 4. Okay, so I have -2 is equal to 4 pi dh dt. So dh dt is equal to -2 over 4 pi, which is -1 over 2 pi. And the units here, since this is h was measured in inches, and our unit of time was minutes. So this would be an exact value answer. If you wanted to give a decimal answer, -1 divided by 2 pi would come out to -0.1592. 0.1592. And again, that's negative. All right? And one thing we want to just make sure is that we do, in fact, get a negative answer. And if we go back to the original diagram, we should be able to tell that DHET is negative because if the liquid is flowing out of the cone, that means the water level is going down, or the liquid level is going down. So we should have a negative rate of change here. Okay? And again, I want to re-emphasize that the reason we need to do this whole proportion setup, when we look at this smaller triangle, the green triangle, or this part in here, the radius is not going to stay the same. As the liquid level goes down, as it goes down like this, the radius gets shorter. As it goes down to here, the radius gets shorter. So that radius is not a fixed radius like the 4 inches at the top is. All right, so whenever you have a cone, you're going to need to go through this process where you have to do the proportions shown over here and then replace one of the variables. Okay, I hope that this was clear.